Hi, welcome to a new video. Today we want to talk about sparse matrices in the coordinate format. We want to introduce this format and then later on implement it in the C programming language. The coordinate format is one way to save sparse matrices and to save on the memory footprint that those sparse matrices take on your computer. In short, we also denote COO. The idea of the coordinate format is probably the most intuitive. So instead of saving the full dense matrix, we are only saving the position and the value of the non-zero entries in our matrix. So let's note this down. Save position and value of non-zero entries. This then means we have the following global variables. Global means that they are independent of the size of our matrix. And we have to save the number of rows, which takes us one integer. We have to save the number of columns, which also takes us one integer. We have to save the number of non-zero entries. This is also one integer. I will denote the non-zeros as n and z, the number of non-zeros. And then we also, of course, have to save the values. This, for example, means we need the I coordinate, and we need this n and c times, and this is, of course, an integer. We need the j coordinate, and we need it again, n and c integer. And then, most importantly, the values itself, which takes us n and z doubles. And let's imagine, for example, we have a 64-bit long integer, so then it has the same length as a double value, so like 8 byte. Then it takes us 3 times 8 bytes for the global variables, and we need 3 times n and z times 8 bytes for the values. Okay, let's look at an example. Here we have this matrix. And we see, well, we have, first of all, let's address the global variables. We have 1, 2, 3, 4, 5. We have 5 rows. And we have 1, 2, 3, 4, 5 columns. Let's count the number of non-zero entries. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 11, sorry, and 12. So we have 12 n and z. Number of non-zeros is 12. Okay, then let's note down what our value arrays are. Therefore, I will introduce something I will call the the n and z idea, or the number of non-zeros ID, so the position in our arrays referring to this particular value that we want to save down. So this goes 1, 2, 3, 4, 5, and this goes all the way to 11 because we have 12 number of non-zero entries. And then we save the I, we save the j, and we save the value. Okay, let's get us some horizontal line here. Great. So let's try to get this down. In the position 0, 0, so position 0, 0, we have the value 2. Position 0, 1, 2, 3, position 0, 3, we have the value 2 again. Position 1 and 0, we have the value 3. Position 1 and 1, we have the value 4. Position 1 and 2, we have the value 2. And position 1 and 3, we have the value 5. And this, of course, goes on in this particular way. And that's how we save our matrix. Next question is how to do a matrix vector product. So we need a description of how to do matrix A multiplied with vector B equals vector C. Let's first start with how we would do this with a dense matrix as a reference. Okay, what is the typical way of doing this? We need two nested loops. So we start with iterating over the rows, saying I goes from 0 to the number of rows. And then we set the value of C at this position to 0. And then we iterate over the columns. And then, of course, we have our actual operation. C at the position I is A at the position I, comma j times the oh, sorry, this is incorrect. So we need to, of course, have a summation here. So it's C at the position I plus A at position I, comma j times the value of B at position j. Then we end our loops. And this is the pseudocode of how to do a dense matrix vector product. Then let's look at our sparse or coordinate sparse. Okay, how should we do this? Well, technically we can't iterate over the rows and the columns anymore, but we do have three arrays which are identical in size. So we could technically iterate over them and make use of the indices that we are getting out here. Okay, let's do this. Let's assign ourselves a variable, let's call it nnsetId, which goes from 0 to the number of non-zeros. Oh, maybe before we do this, let's put the following code here. I goes from 0 to n rows, and this code just sets our vector to 0, and now we are doing our nnsetId from 0 to the number of non-zeros, and then we can access our arrays quite easily. Maybe let's give them some names. Let's call this array, that's the I array. Then let's call this the capital J array, and let's call this the capital W array. Okay, then we can get back the I and J that we used here as iterator variables by accessing the I array at position nnsetId, the J at the J array at nnsetId, and let's call this a small v, and this is the value array at the nnsetId. And then we can go on and do our actual multiplication, which is really similar to what we have here. C at the position I is C at the position I plus, and now our A at ij is a v times, and B at position j we can just access. And then we end our for loop, and this is how we would do this in pseudocode. Okay, now we are in code here. I have a really simple C file where I already created some of the boilerplate stuff. What we want to do here is define our data structure for our sparse matrix in coordinate format, then have 4 functions associated first with the creation, then printing the sparse coordinate matrix, then a matrix vector product, and in the end we want to free the matrix. Okay, let's start with the data structure. What do we need here? First, of course, we need to define the number of rows. We need the number of columns. We need the number of non-zero entries. Then we have an array of row indices, and we have an array of column indices. And last but not least, we have an array of doubles that we call the values. Our three global variables and our three variables that are associated with arrays. Okay, let's go down to the main function. I already prepared the stuff that we had in our previous sheet. We have a matrix with 5 rows, 5 columns, 12 non-zero entries, and of this format. And I just created a random vector 1, 2, 3, 4, 5 for our matrix vector product, and an empty vector for the result of the product. Okay, let's take the interface of the functions and put it down here. First, what we have to do is create the matrix. So what we do is we call the function create sparse coordinate, and this takes the matrix A, it takes the number of rows, it takes the number of columns, it takes the number of non-zero entries, and it takes an object a COO that we first, of course, have to create. So we instantiate a new sparse coordinate matrix, and then we have to hand it over, and of course we need a pointer, so we have to dereference it. Then, last step, we want to free it. So that is what we do first before we do anything else. And here we take a reference to our matrix once again. Then let's quickly implement the creation and the freeing. So create sparse matrix. What do we have to do? We have to first, of course, translate all the variables into our new object. So we have a COO, and the number of rows is, of course, the number of rows. Then we have a COO, the number of columns is, of course, the number of columns, and a COO, the number of non-zero entries is, of course, the number of non-zero entries. Then we have to allocate memory. So we have to allocate for the row indices first, and we do a calloc, and we have to allocate n and c integer or size t variables. Same for a COO for the column indices. We have to allocate number of non-zero integers, and then we have to allocate our values. Same strategy, we have to allocate n and z size t variables. Here we go. Okay, now we have our arrays created and we have to fill them. And one easy way to do this is to go over the matrix row by row, column by column, and look if it is a non-zero entry, and then save it into our matrix or into our sparse matrix. So let's start. So we have an I iterator that goes from I to the number of rows, and it just a simple iteration. Same here, we have a j iterator that goes from 0 to the number of columns. And then we have to check, is the value at this position, we have to check if the value at this position is, let me write this down, if this is unequal to 0. Okay, and if this is the case, then we have to save it down. Then we put this into a COO, into the row indices, row indices, and okay, at which position? And of course we need to have some sort of a running variable that shows us at which position or which non-zero ID we are. And let's call this the NNZ ID, and this starts of course at 0. And here we plug it in, NNZ ID, and at this position we put our I, and the coordinate matrix at the column indices n and z id is a j, or is a small j, of course. Remember, like, the row indices is what we call the capital I, and the column indices is what we call the capital J. And of course, we also have to save the value, and we do this here. Values at n and z id is the value at our position that we are currently looking at. And last but not least, we have to increment our non-zero ID in order to advance in our arrays. Okay, that's it. And now we are done with the creation of our matrix. Let's skip over the print and the matrix vector product and first do the freeing. And what we do here, of course, since we allocated memory on the heap, we are freeing it, and we are freeing it in this way, that we first free, of course, the row indices, then we free the column indices, and lastly, we free the value in the array. Here we go. Okay, now we have a first, this is the plural, and now we can compile this, give it a first try, and run it, and it works. At least it works, nothing prints, no error. That's a good start. Okay, next we want to print our matrix. Print sparse coordinate matrix, and we hand over the coordinate object. What do we have to do in order to print it? So remember, we have our free arrays which are of equal length. So what we can do is we can iterate over them and print out the coordinates together with the value. So let's start with making it a little neat. Put in some spacing here, and then let's get ourselves a header of what we want to print. So we want to print the row index, the column index, and the value. And then let's make it really neat. Okay, then let's start iterating over our non-zero index, going from 0 to the number of non-zeros. And we are incrementing. That's the way it goes. Okay, let's defer our I. And our I is, of course, we are checking at the row indices at the non-zero ID. And the J works similarly. We check on the column indices at the non-zero ID. And to get our value, we check the value array at the non-zero ID. And then we can print it out. And we first wanted to print an integer value for our row coordinate, an integer value for our column coordinate, and we want to print a double value for the value that is inside of that we actually saved down here. And let's put it down. And first we need our I, J, and then the value. And that's already it. So we put it down here. Okay, let's check. Compile. And we have an error. Let me see. Where we have it here. Okay. Of course, I used fprintf instead of printf. That's not good. And there it goes. And that's what we print out. Maybe we should have put in a line break here. So we have at position 0, 0, we have the 2. At position 0, 3, we have the 2, and so on. Perfect. This works. Okay, last step. Let's do the matrix vector product. Matrix vector product sparse. What does it take? It takes our coordinate matrix, it takes an vector x, and of course a result vector that I call ax. And in the end, let's also quickly write down a function that is printing out the result vector, and this is incorrect again, and here we have here we go, and there we want our ax at position I, and so we can check whether our result is correct. Maybe put some space in here, and that's it. Okay, let's implement what we have to do, and that's what we wrote the pseudocode for. So let's get this down. First up, we have to set our array to 0. This is not correct, so that's how it goes. N rows. And we set our resulting array to be 0 at this position, and then we are iterating over our non-zeros. Again, same story. And here we have to iterate this variable, increment this variable. Perfect. Okay, same point. We can maybe already copy this down. We can extract this from our free arrays. And then the rest is fairly simple. We know that the result at position I is the result at position I plus the value times our vector at position j. And that should be it. Let's see if it works, and it runs. And the result is 10, 37, 122, 94, 70, and this is indeed correct. You can double check this, and that's it.